on the screen here, example 5 says use the Pythagorean theorem to find the distance between these 2 points. Now, normally, if I asked somebody, hey, find the distance between 2 points, you might say, okay, where's my ruler? You know, and like slap down the ruler right there and say, okay, this distance is, it looks like about, I don't know, 14 inches on the screen. Or you guys that are watching at home on your monitor or whatever, you might say, all right, it looks like two inches on the screen. So that's obviously not what we're talking about. We're talking about how do I find how many units, how many tick marks there are between these 2 dots. I say use the Pythagorean theorem, and yet, Lewis, what do we know Pythagoras has to do with? Yeah, Beckham triangle. And yet on this screen, I don't see no triangles. Okay. So what I want us to do is I want us to approach this sort of through the mindset of, I remember when we talked about slope, and when you were calculating the slope of a line. Andrew, tell me what slope is. Slope is blank over blank.
Rise over run.
Yeah, buddy, rise over run. So like when we compute rise, what we're looking at is a vertical change. And when we compute run, what we're looking at is a horizontal change. So like here in blue, I might have my vertical change, and here in green, I might have my horizontal change. And therefore, in orange, I've got the distance, and now, Lewis, what do I see on the screen? A daggum triangle, that's right. I'm gonna burn you so bad. Come on in here. I got this sweet burn lined up ready for you. Hey, Luke, would you like some fish? Say what fish? Would you like some fish?
What fish?
Fish to go with that tarty sauce. Oh, burn. Y'all have heard me use that one before, haven't you? Is that a new one? Sweet. All right. Luke, actually, we're just messing with you. We're going through this, our first example, talking about using Pythagorean theorem. All right, so because I can break down the distance between 2 points into a horizontal and a vertical component, right, now I've got myself a right triangle. And you just got to do a little tick mark counting. Okay, so how long is the blue mark? Or the blue line segment? Yeah, it was 4. And how long is the green one? It's 3. So could anybody off the top of their head tell me what the orange one is? It's 5. How'd you know that so quickly? Yeah, that's one of our Pythagorean triples, a 3, 4, 5 triangle, right? So I know the distance between those 2 points now. Obviously, this is an easy example because it's a 3, 4, 5. And I drew it out, and drawing it out is nice. I'm a visual guy, you know that. And it sometimes the drawback of that, no pun intended, is that it takes too much time, okay? So one might say, well, you know, what if it wasn't a Pythagorean triple, or what if I didn't have that triple memorized? Could I still figure out that distance? Absolutely. If I wanted to call that distance d, that is d squared equals 4 squared plus 3 squared. That's the Pythagorean theorem. 1 leg squared plus 1 leg squared equals the hypotenuse squared. If I don't know what the hypotenuse is, I'll just call it d for distance, right? And let's see if we can figure those out. That's 16. That's 9. Combine that, you get 25. All right, if d squared equals 25, then d equals plus or minus 5, because we would just, what, take the square root of both sides. And when we take the square root of both sides, we remember there's a plus or minus. And because it's distance, I'm throwing out the negative one as an extraneous solution. I'm saying, no, we're not going to say, I don't live negative 5 miles away from here, you know. So we would say that distance is 5. So if it's not a Pythagorean triple, that's what we do. We use the Pythagorean theorem, we set it up, and we knock it out. Okay. Any questions on example 5? Pretty easy, right? Now, as typically happens in mathematics, when we have to do something that is easy over and over and over and over and over and over and over again, mathematicians get bored and they say, hey, let's automate that process. We saw that with the quadratic formula, did we not? Okay, like mathematicians got sick and tired back in the day of saying, okay, I'll complete the square and use the square root method on every stinking quadratic equation that I'm solving. And then finally they devised the quadratic formula and said, well, that's just what we're doing every time, so let's just plug in x equals the opposite of b, plus or minus blah, 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 blah. Well, here with this process in red, they said, look, we're sick of dealing with this. Let's automate it. Okay, so they came up with what is called the distance formula. And you and I are going to discuss what they came up with. I got it in the blank right here, so you don't know what it is just yet, but we're going to work through it. Now, it came from the Pythagorean Theorem, and we know the Pythagorean Theorem, right? We know, for example, that the Pythagorean Theorem relies upon a right triangle. And we just got through talking about how the right triangle can be drawn by doing sort of that rise and that run that Andrew was talking about. Okay, but I wrote it up sort of strange over here. I used this little Greek letter. Does anybody know what that Greek letter is? Anybody know what that little Greek letter is? Go ahead, Paul.
Delta.
Very good. It's delta. In class, what does delta stand for? Ooh, somebody's going to try and say it. I heard it. Change. That boy, Quentin. See, I knew Quentin. I knew it. I knew you were going to be the one to say change. Very good. And so delta stands for change. I'm an idiot. Good grief. Y'all yell at me when I do stupid things. What? Anybody see what that stupid thing I did? I put delta x over here, delta y over there. I was talking and writing at the same time, which of course is usually not a good idea. This is delta x. And this is delta y. Okay. So delta means change, right? So delta x here in green is my horizontal change. That's my quote run. And then delta y is my vertical change. That's my quote rise, okay? So from Pythagoras, we would say, well, delta x squared plus delta y squared equals d, distance. All right? James, I'm going to ask you a strange question. Have you always been your current height? You weren't born, how tall are you right now? Roughly. Well, let's say 5'6", 5'7", I don't know, whatever. We're going to round up. We'll say 5'10". There you go. Attaboy. The eyebrows got me. You haven't always been your current height, okay? 10 years ago, I would wager that you were much, much shorter. How could we find the amount of change in James's height from back, are you 15 yet? 14. When he was 4, and now that he is 14. How could I calculate the change in his height? What would I do, Reed? Very good. I'm going to subtract one height minus the other height. That's how we measure change. If I wanted to measure the amount of change in my bank account balance from before my wife went down to Orlando and after my wife went down to Orlando, I would do a subtraction, okay? So when we talk about delta x, and I want you to go back, this is a good exam review, I want you to go back and think, how did we calculate slope? What was the formula that we used regarding these two arbitrary points? Drew? No. Slope was rise over run, so change in y over change in x. But let's get more specific. Think about my example with James and the subtractions. Jack. Okay, again, no, thank you. That's the equation, but I want to know, like, how do we calculate m? How do I calculate the slope between 2 points? That's where we're going. Lewis. So now let's tie both of those comments together, what Drew said and what Lewis said. So Drew said, hey, it's rise over run is delta y over delta x. And then Lewis said, well, delta y is y2 minus y1. That's change. That's James' height now minus James' height then. So if I want to calculate delta x, instead of counting tick marks, I can simply subtract the x coordinate of one point minus the x coordinate of the other point. Okay? So delta x is actually x2 minus x1. And delta y is y2 minus y1. Okay? And so when we replace delta x with that and delta y with that, And then we say, let's get d by itself. By the way, Ben, how do I get d by itself? D is being squared. What do I do to undo a square? Very good. So now, y'all, here is my distance formula. x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And it looks way more complicated than it is, okay? All you're really doing is you're calculating the horizontal change and the vertical change. You're squaring both of those. You're adding those two squares together, and then you're taking the square root. That is what it's called, our distance formula, okay? And I say down here, smiley face. I want you to memorize this as soon as possible. All right? Memorize this as soon. Mossy, can you see that better? Memorize that as soon as possible. Hey, let's use this distance formula. I'll give you your first example of using the distance formula to find the distance between these 2 points. Now, remember that the distance between 2 points is just simply a number. So you're going to tell me Grove's going to say like 7, okay, or whatever that number is. So your answer should be just a number, okay? I want you guys to try that one out. Use the distance formula, and if you're like me, if you're a visual person, you want to graph it out first, feel free, man. Draw the picture out, plot the points, count the tick marks. You can do it that way, but I also want you to practice using the distance formula. Over the years, as you guys, as I've been teaching this topic for years and years and years now, every year I give students the option. I say, you figure out what works for you. Are you a draw router? Or are you a formula guy? And usually about half the class likes to draw it out and count tick marks. The other half the class likes to plug and chug in the formula. And I'm fine with either one. Okay? I want you to be comfortable using whatever works best for you. I'll give you about 30 more seconds. All right. Now, as I mentioned, I'm a draw router. And so here's what this problem would look like if I draw it out. One, two, three, 4, 5, 6, 7, 1. There's that point. And then 1, 2, 3, 4, 2, 3, 4, 5. There's that point. All right. And I want to find the horizontal change and the vertical change. You see how long this is taking, right? And that's okay. Now let's see here. 7 to the left and 4 to the right. That's a horizontal change of 11. Let's see here. From 1 to, what is that, 5. That's a change of 4. So I'm counting my tick marks. It's a 4. There's D. So D squared equals 4 squared plus 121. What is that? 137. I'm going to take the square root of that to get rid of that D. And I'm not going to use the negative, of course, since we're talking about distance. And there we go. Now, that's not too bad. But that sort of takes a little bit of time, right? And you might, actually, I did. Oops, I didn't include my 1 there. Either yesterday or the day before when I was teaching the freshmen this topic, I miscounted my tick marks. I felt like a goober. But I miscounted my tick marks and didn't get the right answer. So, there are drawbacks to this technique, although it's fine if you want to. But the distance formula, the distance formula is much quicker. Now, if I wanted to say x2 minus x1, I could say 4 minus -7. That's plus +7, so that's 11. And then 5 minus 1, that's 4. And again, I get square root of 137. But you'll notice there wasn't any fiddle farting around with picture or plotting points. It's just wham, bam, thank you, ma'am. Plug it into the formula and go. All right. So any questions on example 6? Read. Yeah, great point. I was actually read, smattering there. I was about to bring up that same point. It doesn't matter which point we call x1 and y1 versus x2 and y2. It doesn't matter which point we call the quote first point or the second point. And unlike calculating slope, it actually doesn't matter about being consistent here either. Like I could call this my first point for the x coordinates. I could call this my first point for the y coordinates. It really doesn't matter. Okay, let me show you what I mean. Like if I said, I'm going to drag this down so I can actually reach it. So like if I said -7 minus 4. Class, what's -7 minus 4? -11. But what is -11 squared? The same thing. I got you right here, William. The same thing as +11 squared. Okay? And then if I wanted to come back over here and say, hey, what's 5 minus 1? Or what's 1 minus 5? Again, to Reed's point, it ain't going to matter at all because we're squaring it. Okay? It's a real good point to be made. All right, it's a great question there, Reed. Thank you. Anybody else? All right, let's rock and roll on down here to this example, and we'll probably wrap class up with this example, maybe. I don't know. We'll see. This is a classic 3-for-1 special right here. You get to use the distance formula 3 times in this problem, and oh, yeah, it'll be a good opportunity for us to practice. Now, it says classify the triangle whose vertices are A, B, and C. I went ahead and plotted those out for your viewing pleasure. Okay, you don't have to graph them out. But what I thought we might do is draw ourselves a little picture here. I'll use red for AB. We'll use blue for BC. And we'll use green for AC. Okay. And so what we're going to do is we're going to use our distance formula 3 times. Use our distance formula 3 times. And when it says classify the triangle, what I've got typed in here are the words isosceles, equilateral, scalene, and then I've got obtuse, right, and acute. So can I just go right across the class here and pick some guys to help me figure out what that means? Okay. Alex, can I start with you? What does isosceles mean? What kind of triangle is an isosceles triangle? All right. Let's throw it over to Paul. Paul, what's isosceles? So a triangle with exactly 2 congruent sides. And congruent means same length, right? Very good. All right, so isosceles would mean that, now I think from the picture it's pretty obvious, right, that the red and the blue are not going to be the same length. And that the green and the blue are not going to be the same length, right? But is it possible that maybe the green and the red are the same length? Okay, so visually I'm thinking, oh, maybe that is an isosceles triangle. Maybe there is exactly 2. I know it's not equilateral, Joey. Why not? Because with an equilateral triangle, all of the sides are the same, okay? But it might be scalene. George, what's a scalene triangle? Very good. So a scalene triangle has 0 congruent sides, right? They're all different, okay? So those first 3 words talk about classifying a triangle based on the side lengths, and you all need to know those are good general math words, right? Isosceles means exactly 2 congruent sides, equilateral means exactly 3 congruent sides, and scalene means no congruent sides. Right? What does obtuse mean? Let's see here, Will Edwards. What does obtuse mean? Okay, so an obtuse triangle is going to be where there is one angle that is greater than 90 degrees. Just like he said with his hands, visually speaking, an obtuse triangle means there's one angle that's one angle in the triangle that is more than 90 degrees. All right, class, we should all know what a right triangle means. What does a right triangle mean? We're going to have an angle in the triangle, an interior angle equal to 90. And then let's see here. Masi, what does acute triangle mean? Correct. All three of my triangles, interior angles, are less than 90 degrees. Good. So those are some great vocab words. You'll need to know those for next year. You guys that are, you're all going into geometry, so you want to know what those words mean. Now, some of you alpha dogs have probably already started running some numbers now that I've been beating around the old bush talking about these vocab words. And I hope that you have, because I'm about to run this at pace. Now let's see here, A and B. So we're going to do A, B. So the change in X, that's 7, right? Now, am I actually subtracting or am I doing it in my head? I looked at -4 and I looked at 3 and I thought -4 and 3 on a number line are 7 units apart. Okay, so 7 squared is 49. All right, and then I think -1 and 6, how far apart is that? 7 again, so 7 squared is 49. And so that's going to wind up being 49 times 2, which is 7 square root of 2. So line segment AB, his distance is 7 square root of 2. 7 square root of 2. Now, if you want me to go back through and use like, wait a minute, Coach Morgan, what? Just remember, 49 plus 49 is 98. 98 is the same thing as 49 times 2. We can split the square root of 49 times 2 as the square root of 49 times square root of 2, and that's 7 square root of 2. See how that nice, neat little train of logic works its way right on up that track? Okay, so like if in the back of your mind you're like, what? Make space in your notebook for the explanation. And if I give the explanation, that's great. Kudos, write it down. If I don't give the explanation, then you go home and when you are studying, you figure it out. Okay, I'll pick on Jake. Not that Jake didn't know this already, but like let's just say like Jake sitting here in class is like, wait a minute, what the dump? How did he get from here to here? And so if Jake has that question, Jake needs to leave a little space in his notes. And then when Jake's studying tonight, he's going to say, now, how did he, beard scratch, how did he get from here to here? And that's where some good studying occurs. You can look it up. You can go back in your notes. You can call a buddy. You can figure it out for yourself. When you do that, you learn better, okay? So I don't have a problem explaining anything to you guys, but I want if as you get older, if your teacher doesn't explain something that's like background, like let's say Mr. Perry next year doesn't explain the algebra steps of how to get from here to here. He just says you start here and you get there, and he doesn't have any space in it. You make some space. You say, hey, I'm going to figure out what he did, and then refresh and remind yourself. Say, oh, yeah, I remember Coach Morgan taught us that. All right. BC, that little teeny tiny, cute little segment right there. Let's talk about its distances. All right, so BC, the distance between 3 and 2 is 1. 1 squared is 1. The distance between 6 and 7 is 1. 1 squared is 1. So BC is just going to be square root of 2. All right. And then how about AC? How about we go from A to C? Now let's see here. Y'all help me out, class. From -4 to 2, what's the change in X?
6.
Very good. 6 squared is 36. By the way, don't fall prey to the temptation of forgetting to square. Remember, it's Pythagoras. One leg squared plus the other leg squared equals the hypotenuse squared. So the distance formula's got the squares. We're just doing those in our heads. What's the change in Y from -1 to +7? That's a change of 8. 8 squared is 64, which, by the way, I know 36 and 64 add up to 100. Square root of 100 is 10. So the line segment AC is 10 units long. So can you help me classify this triangle based on its side lengths? What do y'all think? Scalene all the way, baby. Scalene all the way. Because we got 3 different answers. Okay? So we just used the distance formula 3 times. This is a good example of just practicing doing the distance formula. James? You know, that's a fabulous question. I'm going to highlight something. So 7 times the square root of 2 is the same thing as the square root of 98, right? You agree with me on that? That's where that came from. Okay. The square root of 98 is real close to the square root of 100, is it not? It's just a little bit shy. It's not quite there. What is the square root of 100? 10. So the square root of 98 we might approximate as like 9.9, right? It's an irrational number. 7 square root of 10, 7 square root of 2, that is real close to 10, but it's just a little bit shorter. It's a little bit shorter, okay? Now, based on our discussion of the three sides, we conclude this one is certainly a scalene. And now if we talk about the angles, we've been talking about right triangles, and right triangles have a hypotenuse. The hypotenuse is always the what? Always the longest or biggest side, okay? And if therefore 10 is the biggest side, James's question, right? Where we said 10 is just a little bit bigger than 7 square root of 2. Then what's the biggest angle? A, B, or C? Very good. The biggest side is across from the biggest what? Angle. So angle B is going to be the one that I investigate to see whether or not it is 90 degrees. Okay. So in order to do that, I'm going to use what's called the converse of the Pythagorean theorem. Right? You and I have talked about the Pythagorean theorem for a good little while. Remember what it says? It says if you have a right triangle, then the sum of the squares of the legs equals the square of the hypotenuse. Well, fellas, how do I prove that something's a right triangle? I work it backwards. The converse says if you have a squared plus b squared equals c squared, then you have a right triangle. Okay? So let us check, does one leg squared plus the other leg squared equal the hypotenuse squared? Okay, so in other words, does the Pythagorean theorem hold here to give us a right angle, a right triangle? Let's check and see. Who could do square root of 2 squared? Luke, can you do that for me? What's the square root of 2 times square root of 2? Square root of 4 is? Square root of 4. Other direction. There you go, that boy, 2. And another way of looking at this is just to say, oh, look, squaring the square root, they cancel each other out, and you're left with 2. Okay, good. Let's see here. Jack, can you do 7 square root of 2 times 7 square root of 2? Very good, very good. Because you square the 7, that's the coefficient, and you square the square root. And again, that gives you 49 times 2, or 98. And so now, what do we say? It most definitely does work. So therefore, what conclusion would you reach about this triangle? It is a right triangle. Okay. Now, you'll learn next year that if that number over here, if the would-be hypotenuse squared was too big, what does that do to my 90-degree angle? If it's a 90-degree angle and the hypotenuse is, just too big, what kind of triangle does that make it? Obtuse. So if 2 plus 98 had not equaled enough, if this left-hand side had been too little, then you would have had an obtuse triangle. And then if it had been too much, if this number had not been big enough, then it would have been too short, and we would have had an acute triangle. Okay, all done? Sweet. I'll see you here in a little bit. So, fellas, as we work through this kind of example, it is a great opportunity to practice your Pythagorean theorem, practice your distance formula. Are there any questions on example 7? No? Okay. I'm going to do something crazy. I'm going to give you something else new right here with 2 minutes to go. You don't have to write all this down. Just get this formula down. Write this formula down, and let's talk about it. Okay, Charlie, can you write and let me talk to you same time? All right, so Chuck's writing. Charlie, I'm going to give you 2 tests this year. Those are the only grades you get. Each test is worth the same amount. How do you figure out your average at the end of the year? Precisely what we're doing here. To average 2 values arithmetically, you add them up and divide by 2. So the, quote, midpoint of a line segment isn't a value like the distance is. It's not just a number. It's an ordered pair. It's a point. The coordinates are easy to find. To find the x-coordinate, you just average the x-coordinates of the endpoints. To find the y-coordinate, you just average the y-coordinates of the endpoints. Okay? So like that's what I say over here in these bullet points, is that to find the midpoint, really just average the x-coordinates and average the y-coordinates. Super simple, super easy. Okay? Have you got your formula written down? All right, so like check this out. I'll show you what I mean. Super simple. This will take 30 seconds, I bet. Okay? So we want to find the midpoint of line segment AB. Now, could I take the time and draw it out? Certainly I could. That's my prerogative. However, should I use my picture to tell me what the midpoint is? Say no. No, certainly not. Because as you've seen throughout the year, are my pictures always super precise and to scale? No. Paul, you got a daggone problem with my picture drawing skills? No. As much as I try to be a good picture drawer, it's not going to, I shouldn't use the picture to tell me my answer. However, can we average these x coordinates? Let's do that. So the average of 5 and 1 is 3. If I ask you what the average of two things is, you add them together and divide by 2. So you guys that said 6, you just forgot to divide by 2. The average of the y-coordinates is 2. And that's the midpoint. Isn't that easy? Isn't that nice? Right? It's almost as nice as if Will Perone would ever get his stinking haircut. Boom, roasted. Pacey, how did I know that was going to be you? Be kind. These two knuckleheads out here told me something about y'all the other day. They said, man, these 8th graders sure are not very social. They sure don't talk very much. I want y'all to all say hello to these fellas. At 1, 2, 3.
Like 3 of them didn't say anything.
I know. Hey, look, I'll see you guys on Monday. We'll pick up with more of this discussion then. Great job. Live Jesus in our hearts. All right. Thank you so much, fellas. Y'all be good. Have a great weekend. Anybody coming to graduation?